I've started the streaming, sir.
Thank you. So very good morning and welcome to this live session number 4. Like the previous live sessions, what I'll do is I'll quickly browse through the content for this week's lectures or the week's discussion. And then I'll stop wherever there were questions on the Q&A session. So we have noted down those questions and we will discuss them in this live session. Right, so let me quickly browse you through the discussion. So today's discussion is on constitutive modeling and also on the application of the theory of continuum mechanics to linear isotropic fluids. So in constitutive modeling, the main aim of the discussion in this first lecture was on the general motivation of these models from a physical perspective as well as from a mathematical closure need. And then we also discussed the admissibility of these models based on the idea of the material frame indifference, that is the frame from which, the model being independent of the frame of the observer, and also from the material symmetry conditions depending on the nature of material you are dealing with. So that should also be respected. And then the idea of thermodynamic restrictions, particularly the second law of thermodynamics, should also be respected when discussing the idea of when proposing or checking for the admissibility of a constitutive model. So we talked about the definition of the model from a physical perspective. So the idea was that depending on the nature of the material, we noticed that the response is different as a result of the causes. So an example was if you're dealing with a rubber or a steel ball, they show different responses. And similarly, if you're dealing in terms of fluids, you're dealing with a highly viscous fluid like honey as compared to another less viscous fluid like water. And there's some materials which are anisotropic in nature like wood, which has a grain direction. So that should also be incorporated in the system of equations through the constitutive models. So we need something other than the balance laws. So we also discussed that the constitutive models, they demonstrate the behavior of ideal materials, not real materials. So real material may demonstrate regimes where different models may be required. So a constitutive model is not a model for a real material. It's more to do with the behavior of the material in a certain range. And then we talked about the mathematical need through the closure problem. So if you count the number of unknowns and the number of equations, you notice that the system is underdetermined. So we need something else, and that something else is the constitutive model. So we discussed that through different examples for fluids and solids. So this is the most general form of the constitutive model that we can have. It includes strain rates, temperature gradient, and some internal variables that incorporate the effect of history. So we then started our discussion with objectivity, and this was shown that we need to have a cause which is an objective tensor. So what that means is, in fact, we showed that through an example and as a question, that if you naively use the deformation gradient tensor F as the cause in your constitutive model, you may notice that depending on the rotation of the observer, the F prime is dependent on the rotation of the observer. So that basically means that your stress may depend on the rotation of the observer. And we are talking about the rotation of the observer. We're not talking about the rotation of the coordinate system in which these quantities are expressed. So they should not change as a result of the rotation of the observer who is making the measurement. So that is the reason we use C, the green deformation tensor, as when discussing constitutive models for finite deformations. So we relate the Pila-Kirchhoff-2 stress tensor, which is a finite stress tensor that is symmetric, with the green deformation tensor C in finite deformations. And then we discussed briefly, very briefly, about material symmetry, where we said that it's not just a matter of the observer making observation, but also about the material as such. If the material is isotropic, for example, then the constitutive model should not depend on the direction of the application of stress or the application of strain, which results in a stress. So the model should be independent of that, whereas for anisotropic materials, there should be some dependence, and that depends on the nature of anisotropy. So again, this is a very brief discussion on these ideas. We're not going to detail. We don't expect you to understand the different expressions of the constitutive tensor for different kinds of anisotropies. It's just a very brief discussion on the ideas of material symmetry. Then we very briefly talked about the ideas of invariance and constitutive equations. So you will notice that in the typical form of the constitutive model, the invariants appear as coefficients rather than some terms of the cos tensor, that is C. So C tensor would appear in the model from the representation theorem, but the terms of C will not appear. The coefficients will include the invariance of C, as we typically see in isotropic tensors. And then we talked about the material symmetry, where capital S, which is the second Piola-Kirchhoff stress tensor, is a function of C, which is the green deformation tensor. So if you apply this idea of rotating your C first and then applying the constitutive model on that, and then rotating the or rather you first apply the constitutive model and then rotate it, so they should come out to be the same. And this is basically where we talked about the representation theorem about the existence of the three invariants, which typically you'll see in the coefficients of the tensor in the expression for the constitutive model. Again, this is a very surface level discussion. As I said that we don't have to go into detail of how this results in. There was one question about how can we get the different coefficients of the fourth order tensor C for different kinds of anisotropies. But that is beyond the scope of this course. All we showed was that from a general 81 component C fourth order tensor, you can go all the way to you can apply the major and minor symmetries, go from 36 to 21, and then all the way to 2 if you have a completely isotropic material. So that's basically what we showed, but we did not show which component of C is what. All we showed was that you basically go down to two distinct components that are required to express the expression for C. Again, this is beyond the scope for this course, and typically it's discussed in mechanics of solids, where you need certain kinds of anisotropies, or in the general course on constitutive modeling, which goes into detail of different kinds of models. Then we talked about the thermodynamic restriction, which is where we applied the Coleman-Knoll procedure. We demonstrated that through this procedure, once we apply that, we can check for the admissibility of a constitutive model, which basically gives us these restrictions, which are, the first one is stress is conjugate to strain. And this is something that's a very interesting relation that we use to define elasticity in general through the expression, through the scalar work function, rather than through a constitutive model in general. And then we also talk about the entropy that you can get from free energy, and finally the dissipation inequality, which appears as a result, which helps us direct our choice for the heat flux constitutive model as the Fourier kind of models. But again, I mean, I didn't go to detail of these ideas, so I won't expect you to understand or know the details of Fourier kinds of models and different other kinds of models. But you should understand where these restrictions are coming from. That's the fundamental expectation here. So if you have a model available with you, you should be able to make sure if it satisfies the thermodynamic restriction or not. So that helps in proposing new models as well. Then we very briefly talked about the rate type versus history of the integral laws. So integral laws are typically what you notice in viscoelasticity, right? I'll open the next lecture now. Right, so next was an elasticity. We went into the elasticity ideas in terms of the models. So we talked about the stress depending on the current state. There is no history dependence and no irreversibility. So completely reversible situation for elastic materials. In contrast, you have plastic materials where it's irreversible, or viscoelastic materials again where some dissipation happens. So this the system is not completely reversible. And this is where we talked about going from in a linear elastic model. We went from 81 components all the way to 21 components. So we applied the ideas of minor and major symmetry. So in minor symmetry, you simply apply the symmetry of sigma and epsilon, which results in reducing the number of unique components required to express the fourth order tensor sigma. And then for the major symmetry case, we motivate the discussion from the scalar potential energy function W. And finally, if we have if you have a completely an isotropic situation, then you know that the fourth order isotropic tensor, we already discussed that. So if you start from the most general fourth order isotropic tensor and apply the symmetry ideas of sigma to it, you get this expression where you have two constants only that are required to express the relationship between stress and strain, and these constants are commonly known as Lame constants. So these constants can be used, you just need two of these. Either you can express as Lame constants or any of the two to, of the two properties that are required to express the constitutive model uniquely. This is where we then generalize the idea to the idea of generalize the elasticity idea through the idea of energy. So we define this energy scalar energy function W, which is a function of epsilon. And for this particular case of linear elasticity, we get a quadratic energy density function, which is expressed as shown here. And from here, we can find, so in general, this is a general approach for any elastic material, that if you have a W that's available for the material, you can find sigma as the derivative of W with respect to epsilon ij's, and that gives us the constitutive model for the elastic material. And for this special case where you have isotropic material, linear isotropic, sorry. For the linear isotropic elastic solids, we have a quadratic energy density, which when differentiated gives the expression in terms of the two Lamy constants as we had seen. So this is demonstrating that you can work with just one scalar um, potential energy function rather than trying to remember the constitutive model for that situation. There was one question here. The question was regarding the derivative. So the question was that if you take the derivative of the first term on the right hand side with respect to epsilon ij, so if I do that, then you basically get an expression where you have the partial derivative of epsilon kk with epsilon ij. The question was that how does that become equal to delta ij? So I can quickly show that. So I'll be writing on the board for this. So the scalar energy, scalar potential energy function W in terms of epsilon components is written as this for the isotropic linear elastic solid. And in general, sigma can be written as del W by del epsilon ij. That's also something we saw from the thermodynamic restrictions, where we expressed instead of the W, we had the free energy, but that's the same idea. And if I take the derivative, what if I take the first term now? So lambda by 2 is a constant, and then you have 2 epsilon kk. So that becomes, then you have a 2 epsilon kk times, so this is your sigma ij, del by del epsilon ij of epsilon kk, and then we have a mu times epsilon ij. The other epsilon ij is gone. So if I think the question was about this term, how does this become equal to delta ij? Well, the easiest thing to do is to see the definitions. So del epsilon kk by del epsilon ij actually can be expanded to del of epsilon 1 plus epsilon 2 plus epsilon 3 upon del epsilon ij. Now this is of course a tensor because I and j are two free indices in this expression. So if I write this, then if I try to look at the 1 term, then the denominator becomes del epsilon 1. So the partial derivative of epsilon 1 plus epsilon 2 plus epsilon 3 with respect to epsilon 1 is simply 1. Similarly, the three diagonal components are 1, and the derivative or the partial derivative of this sum of the three diagonal components with respect to any non-diagonal component is 0. So this becomes a 0. In the initial notation, this simply becomes delta ij, which is what we had in the relation in the sigma. Okay. All right, so moving on. Then we generalized the discussion to hyperelasticity, that is nonlinear elasticity, which typically you see that for finite strain settings, so for finite situations, nonlinearities are visible. And this is where the general idea of an energy approach shines. So we can express our uh, stress tensor in terms of the derivative of the energy potential. In this case, since we're dealing with finite strains, so we deal with finite stress, which is pK2. And there's a relationship between the Cauchy stress tensor and pK2, as we already have discussed in the past. Right, so we briefly showed this expression that we have between stress and strain in finite strain situations, the equivalence of that from the energy restrictions that we had discussed in the previous lecture. And then we demonstrated a discussion of hyperelastic model through a particular kind of model that's called the Neo-Hookean model, which is used a lot for polymers and rubbers or soft tissues. So in this case, the model is expressed, the W function is expressed as a sum of the shear and volumetric terms like this. And then a similar approach, if you have a W available, then we can get pK2 or the stress by taking the derivative of W with respect to CAB, the individual components of the green deformation tensor, the strain tensor C. And then we can get the Cauchy stress tensor using the relationship between pK2 and sigma. Now, there was again a question here. By the way, I just forgot to mention that. So there was a slight error, although that does not change the conclusions. So in this slide, one of you pointed out correctly that there is an error in the sign here in the second term, and that's very much correct. I accept that mistake, but still that does not change the conclusion here, because the idea was that the dependence on T dot should not be there to avoid this inequality from being violated. So we say that this term has to be 0, which brings us to the same conclusion. But yes, there was a negative sign which was missing here. And so there was a question here that while deriving this S from this W, if you take the derivative of the second or the third term, basically what you get is you get the partial derivative of the Jacobian with respect to CAB. So how does that become equal to C inverse, or how do you express the derivative of J or log of J in terms of C inverse? So let me show that for completeness. So what we are showing is that Jacobian, which is basically determinant of F, let's write that. So what we want to show is the partial derivative of j with respect to c a b is equal to j by 2 times the a b term of c inverse. So that's exactly what we need, what we needed to express pk2 for this Neo-Hookean material. Let's write the relationship. So J is basically Jacobian, which is determinant of F. And then we also know that C is F transpose F. So what that basically means is that if I write the determinant of C, it turns out to be the square of the determinant of F, which basically is the square of the Jacobian. So these are some definitions we need. So let's, in fact, this basically means that Jacobian is determinant of C to the power of half. Let's start with this expression. Using J equals the square root of the determinant of C, that's the definition. If I take the partial derivative with respect to CAB on both sides, then what that gives is you have determinant C to the power of half, so this becomes half, and determinant C to the power of minus half, and then we have partial by partial CAB of the determinant of C, right? And this is basically half. Determinant of C is Jacobian squared. So this becomes j squared to the power of minus half. So that's basically 1 by j. So it can be written like this, times partial by partial CAB of the determinant of C. That's your partial j by partial CAB. We still haven't been able to express in terms of C inverse, but we'll call this A and we'll come back to this. Let's take a pause here and let's go back to the identity and that we had in fact proven in the live session 3 and also used in balance laws. That was that the time derivative of determinant of A is the trace of A dot times A inverse, inner product of that, times the determinant of A. This can also be expressed in the variational form. That is, we just see the change in one quantity with respect to the other. So if you take a slight change in the elements of A, that of course results in the slight change in the determinant of A. So if I was to divide this by delta t, that would basically give me the same expression as above. So we can use this variational form, let's not box it, to proceed. So what I can now do is I can apply this to C. So I get partial determinant of C is trace of partial C dotted with C inverse times determinant of C. So this is how I bring in the C inverse in the picture. So what we'll do now is we'll express it in terms of the initial notation. This is still partial determinant C, and then there's an inner product. So I can write this as the partial Cij, and then you have a C inverse, and then you have a Ji here. So that's basically the trace of partial C dotted with C inverse, and then you have determinant of C here. Now what I'll do is I'll move this to the left hand side. So this gives me partial determinant of C by partial Cij is C inverse Ji determinant of C. In fact, I and J are dummy indices, so for convenience, let's call them A and B. So I will be replaced by A, and J will be replaced by B. So this becomes BA, and now we're very close to what we had to show. So this expression, if I go back up, I was looking. I think I made a mistake here. This should be partial CAB. Right. So we wanted this partial determinant of C by partial CAB, and this is exactly what we have here. In fact, this can be written as and this is C inverse BA times determinant of C. So this we'll call B, and we'll substitute B in A now. So in A we had partial J by partial CAB equals 1 by 2J. So I'll write that again. And then partial determinant of C by partial CAB, which basically now is shown as C inverse BA times determinant of C, which basically is the square of the Jacobian. So this becomes J by 2 times C inverse. Now C is a symmetric tensor, so is C inverse. So we can write this as C inverse AB. This is partial J by partial C AB. And this is exactly what we had to show. Let's go back up and check. So this is what we had to show, and we have shown this. This, let's call this 2, and this was 1. Right. So this was one of the problems in the Q&A chat box. So I hope this is clear. So let me reshare the slides and then we'll proceed. Right. Now the next step, we just for motivation, using this sigma that we have obtained for the Neo-Hookean material, we applied two different approximations. One was for the incompressible limit, which gives this kind of an expression for incompressible situation. And the next was for a small strain limit. But remember, this small strain was applied to the general form, not the incompressible limit, as there was a confusion. And when we do that, we get this expression below for the sigma, which exactly is what we have for isotropic um, small strain situations, the linear isotropic model that we have. So this is, if I just go back. So what we started with is for a hyperelastic model, that was the constitutive model. So this was for an isotropic hyperelastic material, the Neo-Hookean model. We already had assumed the system, the material to be isotropic, but it was hyperelastic, so it was a finite situation. Now, if that's a more general case, right? And if I take the approximation of infinitesimal strain situation, that should give me the constitutive model for infinitesimal isotropic elastic solids. It's all elastic we're talking about. And that is exactly what we have in terms of the two Lamé constants, lambda and mu, in the last expression in this slide. There was again a question here that how do we get this sigma from the general form given on the top. So let's show that as well. So in the general form, we have sigma ij is mu upon j times bij minus delta ij plus lambda times the log of j upon j times delta ij. Here bij is defined as Fia times Fja. That's basically F times F transpose. And also for the small strain limit, what we see is that F in the first order approximation can be written as delta Ia plus ui comma I, and this is something we have already shown in the past. Similarly, C is approximated as delta AB plus twice epsilon AB, and the Jacobian in the first order approximation is 1 plus epsilon cc. So we are still keeping the first order terms, error terms. I mean, there are situations where you might see that j is approximated to 1. That is when you ignore the error terms completely. So epsilon cc is smaller than 1, definitely, for the small strain limits, but we are keeping those because there are situations where you have difference between j and a 1. So if you had approximated j to be equal to 1, then you get a 0. But if you're taking the difference between j and a 1, then to the first order approximation, that should give you epsilon cc. So it's always good to start with the first order approximation, and then towards the end, you can do a zeroth order approximation by ignoring the terms if required. But for situations where you have differences, you should always keep the error terms to start with. Right. So this is, so let me, I think I didn't share my screen. So let me share that. Yeah. So this is the journal form for Neo-Hookean solid, which is isotropic finite case. So what we do now is we substitute these into this sigma. So our sigma ij becomes mu upon 1 plus epsilon kk. Then we have a bij, which is Fia times Fja. Fia is approximated as delta Ia plus Ui I comma A, and then FJA is written as delta, let's call this delta J A, yeah, plus U J comma A. Right, and there's a minus delta Ij, and then you have another term which is plus lambda times the log, natural log of J, which is 1 plus epsilon kk divided by J, which is 1 plus epsilon kk. And then you have a delta Ij. So this becomes, so I can take 1 upon 1 plus epsilon kk common, and then we are left with is a mu times, now we'll open the multiplication here. So we have a delta Ia times delta J, so that becomes a delta Ij. Then you have linear terms, which is u I comma j, and there's a uj comma I, and then you have a second order term, which is u ia times u ja, and there's a minus delta ij term as well, plus lambda, and then we have a log of 1 plus epsilon kk. I hope my screen is visible. There's a message that I'm not showing that. It's an earlier message, right? I hope the screen is visible now. This is lambda times log of 1 plus epsilon kk. Now, log of 1 plus epsilon, where epsilon is smaller than 1, can be approximately written as simply epsilon kk, and then you have a delta ij. All right. Now, what we'll do is in this expression here, we'll neglect that, because we are adding a quantity which is small to a quantity which is very small. So this is approximately equal to the small quantity. So we're taking first order approximation, but on second order. So this goes, and then of course this delta cancels. Now remember, this is exactly the reason we had taken a first order approximation, because now the delta, and that's basically the ones you had, they get cancelled out. So the expression is the error terms. If you had started with zeroth order approximation, then you would have got a zero everywhere, which would not make sense, right? Let's write the simplified expression. 1 upon 1 plus epsilon kk times mu. And now what is this? This is twice epsilon ij from the definition of infinitesimal strain tensor. So this becomes twice mu epsilon ij plus lambda epsilon kk delta ij. And again, now in the final step, what you see is that you're left with a 1 plus epsilon kk. Now epsilon kk would be much smaller than 1, right? So this will now be approximately written as 1, because if you were to put values, you would see that 1 upon 1 plus 0.001 would approximately be equal to 1. So this becomes approximately equal to twice mu. Let's write it in the form that we are used to. Twice, lambda epsilon kk delta ij plus 2 mu epsilon ij. That's your sigma ij. So this is exactly what we have for an isotropic linear elastic constitutive model for small strain situations. Right. There's a question. There's an exam on Friday. It means that we won't have. No, this is a session for both weeks 11 and 12. We'll also cover week 12 here, although we didn't have any question on the chat about week 12, but I'll quickly um, take you through week 12 as well. Right. So this is 53. Now 54, we didn't have any questions. So let me quickly take you through, very quickly take you through it, and then I'll go to the other weeks. So then we talked about fluids, where we talked about the constitutive model for linear isotropic fluids. Now, mostly the fluids are isotropic because they get mixed with each other. There are some long chain molecules where you may see an anisotropy in fluids, but mostly you'll see them as isotropic. So again, a very similar expression as you have for the linear isotropic solids. Then we briefly talked about non-Newtonian fluids, which deviate from the linear isotropic nature. They could be non-linear isotropic, or that could be anisotropic as well. So the most common is power law fluids. We talked about Bingham fluids, where you have a yield stress, where they initially behave like solids, and then beyond a certain stress, they start behaving like fluids. And we check for this yield criteria using the J2 of stress, as we discussed earlier in the octahedral shear stress situations. And we have Herschel-Berkeley, which show a yielding behavior like previous case of Bingham, but they have a nonlinear nature beyond that. We talked about very specific models like cross model, where the viscosity ranges between two different viscosities. And then we then talked about time-dependent fluids like thixotropic and rheopectic fluids, where the viscosity changes or with time, not instantaneously, but over time. We discussed about two important ideas which are used to express the nature of viscoelasticity, that is creep and stress relaxation tests. Then we moved on to the Maxwell model, which is a series combination of these models of Spring and Nashport, and the Kelvin-Voigt model, which is parallel combination of them, which are used to express different kinds of situations. But the most common for viscoelastic is the standard linear solid, because that shows a realistic behavior. So this is, and we also had a problem in the tutorial on that. And then we briefly talked about the fact that we don't do these two tests separately. We do an oscillatory test where the strain varies using a sinusoidal function. And then from that, you can get the nature of the behavior through these moduli, G prime and G double prime. You get the idea about the elastic and the viscous nature of the fluid in viscoelastic fluids. Briefly talked about the Boltzmann superposition principle, the relaxation kernel G, which tells us how the history is incorporated in the material. And there's a fading memory effect. So the recent times have more impact than the previous older times. And then next we moved on to plasticity. Again, plasticity usually is a complete course in itself. In plasticity, we started the discussion with a plastic material, which um, it basically allows you to store the strains. If you take a ductile wire and you bend it, what you see is that after bending, you leave the wire. It comes back slightly, but mostly it stays bent. So that staying bent is the plastic deformation. And then you have a slight, uh, it comes back slightly, so that's the elastic strain. And it's the plastic part, it's the elastic part which helps us relate the cause and the response. But it's the plastic part which is the internal variable that we require for these kind of situations, which in usual cases, you will notice that this plastic strain will result in some sort of hardening. It can also lead to softening, but typically for materials, we notice there's a hardening. So if you bend a wire, you leave it, and the next time you apply, try to bend it again, then you'll see that the amount of stress you require is the yielding stress basically increases, and this is where the idea of yield surface is important. Now we barely touched upon the ideas here, just to give you a feeling of what plasticity is about. But as I said, there's a whole typically a full course on plasticity in universities, so that you need to go into that to study this in detail. One general idea here was that we express the yield surface in terms in a 3D space where the three dimensions are the three. I mean, stress typically is 6 independent components, but if we express that in its principal coordinate system, the stress tensor becomes diagonal with three unique components. So every stress state can be expressed in terms of its principal components, where you have 3 independent components. So we try to express things in a 3D space, um, which helps us understand the yield surface. So yield surface, flow rule, and hardening, they're the three ideas in plasticity that one deals with. And again, yield surface, which are pressure independent, you can always draw things on. We draw everything on the deviatoric plane, which is perpendicular to the hydrostatic axis, because you're dealing with uh, things independent of the hydrostatic pressure. Right? There's a von Mises model, there's a Tresca model, Drucker-Prager model, which is pressure dependent model. We talked about the flow rule and then the hardening, which basically incorporates the change in yield stress because of the history of your straining in the material. We also briefly talked about the Boschinger effect, where the yield surface seems to translate, but basically what that means is that it may harden in one direction and soften in the other direction. So it seems that the surface, if you plot it or you draw it mathematically, it feels that it has translated in the stress space. Right, so this is what we had discussion in elasticity. And now let me quickly then tutorial for week 11 actually was moved to week 12 because we were allowed 5 sessions per week, and because week 11 was quite heavy in terms of the theoretical content, so and week 12 was a little lighter, so we moved tutorials. So this is not an error, it's just that for technical reasons we had to move it to the next week. So in the tutorial we talked about problems where we showed that C is indeed a fourth order tensor, and then the problem was to show that if you start with the general fourth order isotropic tensor, you can get down to your isotropic stress strain constitutive model from that C. Next was we had a Neo-Hookean material, and then we had to show that it takes the linear isotropic form, which is where we did things which are similar to what I showed you in the steps earlier. And the third was on the application of viscoelasticity, where we used a standard linear solid SLS model, and we did some mathematics related to that. So this was a very brief tutorial for the constitutive modeling, and that this is when we moved on to fluids. And in the fluids, we started with, this is just basically the idea of having this week was to demonstrate the fact that we can apply the theory of continuum mechanics as we have learned to different kinds of materials. So we just used fluid. But typically in a fluid mechanics course, this would be the first week that was the last week in our continuum mechanics course. So continuum mechanics basically then gets to a fluid mechanics or an advanced fluid mechanics course, an advanced solid mechanics course, or a constitutive modeling course, or a course on granular material and so on. So this week was just an application of what we learned in this course. So we started with the definition of fluids. Fluids are typically materials which are not able to sustain a shear stress. If you apply a shear stress, they will definitely deform. But the deformation, the amount of the rate of deformation depends on the constitutive nature of the fluid. So the amount of resistance they provide will be different for different materials. Like honey would provide more resistance as compared to air or water, which would provide less resistance. So in fluid statics, we showed that because by the corollary of the definition of fluids, if the fluid is static, that means there is no shear stress acting on the fluid. So that means that any cross section or traction would be normal. So that tells us that we have an isotropic state of stress for static fluids in hydrostatics. And this is what tells us this thermostatic pressure to the mechanical pressure for static fluids. Now for moving fluids in fluid dynamics, we split sigma into an isotropic and a viscous stress part. So it's the isotropic part basically is the part which includes the thermodynamic pressure, and the viscous stress part is the remaining part, which actually we'll see later it comes out to be the divitoric part, but that's after the application of the Stokes hypothesis. So this is where we assume the fluid to be linear, that is Newtonian, isotropic, linear fluid, and then for the isotropic fluid, Newtonian fluids, we get the tau versus d relationship, which is exactly the same as what we had in isotropic linear solids. Now here we applied the condition that the mechanical pressure and the thermodynamic pressure are the same. That's called Stokes hypothesis, and this is the case for most of the fluids. And this is where we get we boil down to just one viscosity coefficient. This is typically what we see in the constitutive model for air or water. And then once we establish the constitutive model for a linear isotropic fluid, we applied that in the balance laws, because remember, constitutive models are required in addition to the balance laws to close the system. And when we did that, we were able to derive the famous Navier-Stokes equations, which are the nonlinear fluid equations. And then we discussed some special cases, particularly the case of incompressible situation, which are very common for water, oil, or even for air at low Mach numbers. They can be approximated as incompressible fluids. So this all is something that you will learn in a fluid mechanics course. But we wanted to show that using the theory that we have developed in this course, you can derive all these expressions as well. And then we talked about irrotational fluids as well, which are typically seen outside the boundary layers in free stream regions, where you can basically solve for a scalar potential phi. And then in the last lecture on fluids, week 12, we applied these equations, the Navier-Stokes equations, to an actual problem of a free surface flow. And through that application, we were able to derive, or we were able to solve for finally the pressure and the velocity field in the fluid. So remember, what's the aim of mechanics? The subject of mechanics is required to solve for the motion due to some forces acting on the system. So in this case, in the fluid, we had some stresses acting on the system in terms of boundary conditions and so on, and we had to find the velocity field, that is the motion of the fluid. So we are able to do that using the application of the theory of continuum mechanics, and that was the intent of this week. That's the end of the course, and then the final lecture was on the summary of the learning outcomes of each and every week. Right. So this is live session 4. So I wish you all the best for the exam, which is due later this week. And if there are any further questions, they can always be sent to the Q&A session, and I'll be happy to reply them at the earliest. Thank you very much. And we can now close this session for recording. Thanks.